Today, we're diving into one of the most fundamental and, frankly, one of the most important components in all of mechanical engineering, the simple but incredibly powerful spur gear. You've seen these things everywhere, right? From the tiny, delicate insides of a watch to the absolute guts of a giant wind turbine. But seriously, don't let that simple, toothed wheel shape fool you. It's hiding a whole world of complex physics. Their one job is a constant, high-stakes battle against some pretty immense forces.
So to really get a grip on that battle, we first have to understand what these parts are and the one absolutely critical job they're designed to do.
At its heart, a spur gear is about as straightforward as it gets. It's a wheel with teeth cut straight across its edge. This is the most common type of gear out there, and it's made to mesh perfectly with another one just like it, letting them transmit power between two shafts that run parallel to each other.
And that's it. That's their whole purpose in life. They take that turning force from one place, like an engine, and they move it to another place, like the wheels of a car. It's all about transferring that rotational energy, and, crucially, doing it efficiently and without any slipping.
Okay, now this is where things get really, really interesting. We're going to zoom way in, right to the exact point where two of these gear teeth touch to see the physics at play. So get this, all of that power, every bit of torque, is transferred through one tiny point of contact. This creates a single, powerful, combined force called the normal force. And as you can see, it pushes diagonally, along a path that engineers have a cool name for, the pressure line. But here's the thing, that one big force doesn't stay as one force for long. For all practical purposes, it immediately splits into two separate components. You've got the tangential force, which is the one that does all the useful work, and then the rest of that energy becomes the radial force, which has a very different and, well, much less helpful job. And this is honestly the perfect way to think about it. The tangential force, that's our hero. That's the force that provides the torque, the one that actually makes the next gear spin. But the radial force, yeah, that's the villain. It does zero useful work. Instead, all it does is try to push the two gears away from each other, which puts a ton of stress on the shafts and bearings.
You know, the source material just nails it with this quote. It really highlights the central challenge for engineers. You've got to maximize the effect of that heroic tangential force while doing everything you can to manage the problems caused by that villainous radial force. So, with this constant battle going on, this push and pull, it brings us to the really high-stakes part of all this. What happens when those forces actually win?
I mean, really think about it. Every single time a pair of teeth mesh, they go through this cycle of intense loading. In something like a high-speed engine, this can happen thousands or even millions of times per minute. All that stress just builds and builds, and that's what eventually leads to failure. And when a gear fails, a car's transmission can just seize up, or an entire factory production line can grind to a halt.
And failure isn't just one thing either. It can show up in a few pretty nasty ways. You know, a sudden impact or just too much overloading can cause a catastrophic tooth breakage, just snapping it right off at the root. Or high stress on the surface can cause pitting, where tiny fatigue cracks just grow and grow into little craters. And if the lubrication fails, well, the heat and friction cause scuffing, literally welding and tearing the surfaces of the teeth apart. It's brutal. I mean, that is a seriously tough environment for any part, right? So it just begs the question, how on earth do engineers design something that can survive this relentless punishment, day in and day out, for years on end? Well, the secret, the real genius of it, is that they don't just design for a perfect world on paper. They design for all the messy, unpredictable conditions of the real world. To do this, they have this key concept called effective load. This isn't just the simple, clean number you get from a basic calculation. No, it's a much smarter, more realistic number that takes into account all the extra stresses a gear is going to face when it's actually doing its job. So how do they get that number? Well, first up, they use something called a service factor. This basically accounts for what's powering the gear and how hard the machine is working. So for instance, a gear in a light-duty setup that's being driven by a super smooth electric motor, it gets a low factor, like a 1.1. But take that same machine and power it with a jerky single-cylinder engine, that factor jumps all the way to 1.5. The harshness of the power source itself adds a huge amount of stress. Okay, but that's not all. Then, they bring in a velocity factor. See, the faster a gear spins, the bigger the impact of any tiny, microscopic imperfection from manufacturing.
This table shows you how a slow-moving, commercially cut gear is treated completely differently from a high-precision, high-speed gear that's been carefully ground and finished to be perfectly smooth. Speed just amplifies every single tiny flaw. And that is the big secret. You take that basic, calculated force, you multiply it by these real-world factors for service and velocity, and suddenly you have the true load the gear has to withstand. That is the number they design for, building in the right safety margin to make sure the gear doesn't just work on paper, but that it actually survives for its entire intended life out in the field.
All right, so let's do a quick recap. We started with the Spur gear's simple job, moving power from A to B. We saw how that creates a single force that splits into our hero, the useful tangential force, and our villain, the destructive radial force. We learned that if that battle isn't managed, it can lead to all kinds of ugly failures. And finally, we saw how engineers actually design for victory, using special factors to account for the very real stresses of the real world.
Which brings us all the way back to the beginning. That simple-looking toothed wheel, it is anything but. It's a precisely calculated marvel of engineering, designed from the ground up to fight and win an invisible, relentless war of forces every single second it's in motion.